let us start looking at light and reflection. So first of all, light is an electromagnetic wave. That means that the electric and magnetic fields fluctuate together while they are perpendicular to one another. So that's a little bit hard to draw, but I'll give my best here. So let's say that we have a three-dimensional, an XYZ coordinate system, and let's say that this is one of the waves. Let's say it's the electric field. So that means that that would be the amplitude of the electric field. Well, the magnetic field is going to be perpendicular to it, so it will be in this plane, and it will look like this. So this would be the amplitude B max of the magnetic field, and that's B and that's E. So that's what we mean by saying that the electric field, so this is perpendicular to the magnetic field, and the same thing in these situations. Now, the electric and magnetic fields are also perpendicular to the direction of propagation of the wave. So if we go back to the previous drawing, this wave would propagate in this direction. That's the direction of propagation. It is actually given by the right-hand rule, where one places their hand in the direction of the electric field. So hand is along the in this direction with fingers pointing up that way, and then bend the fingers in the direction of the magnetic field. So the outstretched thumb will then be in the direction of propagation of the wave. All right, light is a transverse wave. So we've talked about longitudinal waves and transverse waves. And with transverse waves, we've said that particles along the wave move up and down perpendicular to the direction of motion of the wave. Now, based on the range of frequencies of light, we have something called an electromagnetic spectrum. So it describes a really wide range of frequencies and wavelengths. In increasing order of frequencies, we start out with radio waves, AM waves, and that stands for amplitude modulation, FM waves, and that stands for frequency modulation, then microwaves, infrared, the visible spectrum, and the wavelengths in the visible spectrum are between roughly 400 nanometers and 700 nanometers. Then we have ultraviolet, UV, X-rays, and gamma rays. So as frequency goes up, so this is frequency increasing, we also have wavelength decreasing. So frequency goes up, wavelength goes down, so that their product can stay constant, and the product is equal to the speed of light, which is about 3 × 10⁸ meters per second. All right, now one of the things that light does is it reflects. So it bounces off at the interface between two media. So let's say that we have a shiny surface here, and I'm going to draw hash marks on the back side of the surface. And if we have a light beam hitting that surface, it will bounce so that the angle of incidence is equal to the angle of reflection. So these angles are measured from the beam to the perpendicular to the interface between the two media. So this angle here is 90 degrees. And this angle and that angle are the same. Now, one application of the law of reflection is mirrors. So here we have a plane mirror, a concave mirror, and a convex mirror. Again, the back side of the mirror, so the non-shiny side, has these hash marks on it. We will always draw this line that we'll call the principal axis, and then we'll have to define a few terms. So here's going to be a list of them. Let me draw just one mirror here. So that is a concave mirror. And the things that I defined are radius of curvature. So, of course, this concave mirror is part of a circle, a circular surface. So that will have a radius. So then, right in between the center of the curvature and the place where the principal axis intersects the mirror, so halfway between these 2 points, there is another point called the focal point. So F, capital F, is the focal point, and then this distance is called the focal length. And focal length is exactly in the middle of the radius of curvature. So I guess I should put C here for center. All right, now we will place an object in front of a mirror, and our object will look like this. So that's just an arrow, and we're pointing it up, so it may be a person standing right there. We will call this the object distance. So how far away from the mirror the actual object is. Then the object will reflect from the mirror, and it will produce an image. And the distance to that image is going to be the image distance. I'm not going to draw where that image is because we'll draw ray diagrams later, and we're going to look at this again. So there is a relationship between the focal length, the object distance, and the image distance, and that is 1 over focal length is 1 over object distance plus 1 over image distance. Then there is something called magnification. So that has to do with whether the image is larger or smaller than the object. And then the magnification equation is negative di over do. So negative image distance divided by object distance. Now we have a sign convention for mirrors for the different distances. Everything in front of a mirror is positive. All the distances in front of the mirror are positive. All the distances behind the mirror are negative, which makes us think of what happens to a convex mirror. So the convex mirror is part of a circle that actually has the center behind the mirror. So that means that this radius, by convention, will be negative. Since the focal length is on this side of the mirror, the focal length will also be negative. So we have to pay attention very carefully to the conventions of signs. Now, one more thing before we go on to ray diagrams, and that is that images that are formed in front of a mirror are real, because we expect with mirrors that light bounces off a mirror and then goes back along the same side of the mirror. So we expect images formed on the shiny side of the mirror to be real images. And images formed behind a mirror are what we call virtual. So one example of a virtual image is in a plane mirror. If you look at yourself in the mirror, in a bathroom mirror or whatever, that image that you're seeing is actually a virtual image. And the way of thinking about it is that you cannot project it on a screen. So you might want to, put a piece of paper behind the mirror and see if you can capture your image, and you know very well that that wouldn't happen. So a virtual image is one that cannot be projected on a screen. A real image can be projected on a screen. Now, another thing about the plane mirror is that the magnification in a plane mirror is 1. So when you're seeing yourself in a mirror, if the mirror is really perfectly plane, then your image is the same size as you. So the magnification is 1, which means that the image distance is equal to the object distance in absolute value. The image distance will be negative because it will be formed somewhere behind the mirror. And the object distance, we usually always take it positive. We always place an object in front of the mirror, not behind the mirror. Let us look now at some ray diagrams. Ray diagrams will help us identify the location of the image of an object. So first, let's look at concave mirrors. So let's draw the principal axis, and then let's place a concave mirror here, and I'm gonna hash mark the back so I know which is the shiny side of the mirror. Now I'm going to have to identify the focal point and the center of curvature. We don't have to be very precise in terms of, well, where is the center? I think my center is a little bit too far away, which means that the focal point is too far away, but that doesn't really matter. What really matters for drawing the diagrams really well is that this distance and that distance are about the same. They should be exactly the same. We want the focal point to be exactly in the middle between the center of curvature and this point. So this is C, this is F. Now let's place an object. I'm gonna put it over here. That's the object. I will draw a few rays that that are always they're special rays. So these are the types that you'll always have to draw in a ray diagram. So the first one is going to go parallel to the principal axis and strike the mirror. So that goes from the tip of the object parallel to the principal axis, and that particular wave is going to reflect through the focus. So we always like to put arrows on our beams, so the beam goes incident in this way, and that is the reflected beam. Now the second beam is basically the backwards of this. So I'll start with the beam from here, go through the focus, and that beam will be reflected parallel to the principal axis. Something like that. So again, I want to draw arrows for the incident beam and the reflected beam. Now we can draw 2 more beams. I won't, because that will clutter the image. So one of them would go from here to there and then reflect back, so that, oh, maybe I will draw it. So let's look at this. So I'm going to draw the object upside down here, just to help me guide me with my lines. So my third line here is going to go from there. Whoops, let me undo that and get my straight line tool. So it goes like this to this point, and then using the law of reflection, where this angle would have to be equal to the angle of reflection, I'm going to draw the other beam that goes to here. So that's why I drew this upside down image here so that it would help me with these two angles. All right, and then the last beam would be one that starts from the object, goes through the center, and reflects back along the same path. So this is the incident, and this is also the reflected beam. And I didn't put arrows on my red beam. Let's do that. So this was the incident beam, and this was the reflected beam. So now it's a big mess. The point of it is that the image forms at the intersection of the reflected beams. So reflected beams would be this one, this one, this one, and that one. And if I look carefully at this mess, my reflected beams intersect right there, which means that my image will have its tip, so the tip of the arrow would be at that point. So I will have to draw my image like this. So let's see what characteristics this image has. Well, it is inverted because we started out with an arrow pointing up and we ended up with an arrow pointing down. It is smaller than the object, and it is formed on the same side as the object. So it's formed on the shiny side of the mirror, so that makes it real. All right, let's look at another situation for concave mirrors. So I'm going to draw a principal axis here and another concave mirror like that. That's the back of it. And let's say that the focal point is there and the focal length then should be, the center should be there. So focal point, center of curvature. And I will place an object inside the focal point. So now I'm going to have to draw the rays that I drew here. So the first one was a beam coming in parallel to the principal axis. So the green line and the principal axis are parallel to one another. So here is a beam parallel to the principal axis and going through the tip of the arrow, roughly. And that beam reflects through the focus. So it goes back this way. So let me put arrows on them. So that's the incident beam and this is the reflected beam. Then the second beam I had was the reverse of that. So I started out with a blue beam here towards the focus, went through the focus and then reflected back parallel to the principal axis. So blue beam will go through the focus first. So it has to go this way and then reflect back to the principal, parallel to the principal axis. So that's about like that. Let me put arrows on that. So this is the incident beam and that is the reflected beam. I won't draw the rest of the beams because the image gets too cluttered. So the point now is that we know that the image is formed at the intersection of the reflected beams. So this is a reflected beam and that is a reflected beam. So at the intersection of that and this, well, it doesn't really look like these two beams will intersect on the shiny side of the mirror. So what that means is that we'll have to extend the beams on this side of the mirror and then see where they intersect. So let me extend the blue one. something like that. And I would, well, let me undo that. I have to make it a dashed line, so I can't use my line tool. So I'm making a dashed line because the actual beams of light do not travel behind the mirror. So that's what I want to indicate by drawing a dashed line. So then the extension of the of this beam will be going there, and my beams intersect at this point. So I will draw my image. So that's image, this was object. And now the characteristics of the image are, the image is upright now. It is larger than the original object. And since it is formed on the wrong side of the mirror, where it cannot be projected on a screen, then this image will be virtual. All right, let's look at convex mirrors. So here's a principal axis, and let me draw a convex, convex mirror. All right, so with convex mirrors, remember that the center of curvature is on the other side of the mirror, not on the shiny side of the mirror, which means that the focal point will also be on the other side of the mirror. So let's now place an object over here somewhere, and we will draw the same beams. So the first beam is the one that comes parallel to the principal axis, so something like this, and then it would reflect through a beam that would pass through the focal point, but it doesn't actually pass through because it bounces out. So just to aid in my drawing here, I'm going to draw what happens behind the mirror, but actually I have to extend this like that. So that is the reflected beam. This is the incident beam. The reflected beam bounces away from the mirror so that the extension of this beam would pass through the focal point. The second beam starts out from the object and goes in the direction of the focal point, but it doesn't actually pass through to the other side. Only its extension would go that way. And at the surface of the mirror, it's going to be reflected back along parallel to the principal axis. So here we have the incident beam and the reflected beam. So the image is formed by the reflected beam and this reflected beam. Well, they clearly do not intersect on the shiny side of the mirror, so I have to draw extensions to those reflected beams, and I already did for the green beam, but here is the extension for the blue beam. And looking carefully, I see that the two beams intersect right here, so that's the image. Now let's practice a little bit with the other beams also. So remember that there was a beam that passed through the center and kept on going and bounced straight back. So that's the one that I'm going to draw here, and hopefully it will intersect the other beams where I want them to. So, let me grab my tool here, my straight line tool. So it's a beam that would go through the center, but it doesn't make it there. It just bounces back along the same path. So if I were to extend it like this, then my beam would also pass through that point. So my three beams will intersect at that point. So let's see what can we say about the image formed in a convex mirror. So it is upright. It is smaller than the object. And it is virtual because it is formed on the wrong side of the mirror. Let's compare what we've written in these three different places. So for the three different situations for mirrors. We see that an upright image gives us a virtual image, whereas an inverted image is a real image. So that is always the case when you're dealing with one mirror or later on one lens. If you have a combination of mirrors or lenses, that's no longer true. But for one mirror or one lens, if you have an upright image, it is virtual. If you have an inverted image, it is real. So that's just a little trick to remember.